Hello, AP Calculus crew. This is Mr. McCallan, and I just want to tell you that this is the first night that we are trying, or first day we're trying the flipped classroom, and this will be considered to be introductory material, and I'm trying to watch my time so this stays under 15 minutes. So, what I want to first talk about is how the integral, the area under any curve, is considered to be net change. So, generically, we just have a function f of x, and we typically integrate it from a to b, and the area under the curve is just something that we assign a value to. But when we enter the world of applications, and let's just say that we're looking at the velocity graph, and we consider to be integrating velocity as a function of time from a starting value, let's say this is 3 seconds, to 9 seconds. What this really represents is the net change in, and I'm going to put here parentheses, displacement from 3 seconds to 9 seconds. So how do we figure out that that's displacement? Well, the units of velocity are meters per second. Let's just say in the SI system, and time here is given in seconds. When we do dimensional analysis and we multiply meters per second by seconds, the seconds drop out, and the units for area are meters. Now, what does that mean? Well, some people will just say it represents like the amount of meters traveled. It actually represents the net change in displacement from where you were when you started at 3 to where you are at 9 seconds. So, thinking about that, we're going to do example 1 from our textbook. And example 1 gives us a velocity function, and it wants us to understand or describe the motion of the particle. So the first thing we're going to do is I'm going to ask you on your graphing calculators if you can plot that function in the domain from 0 to 5 and get the entire function so you can analyze it. While you do that, I'm going to cut and paste a function from Desmos so that we can analyze it together. Okay, class, so we're back, and if you look at the Desmos graph, what you can see is that this is velocity as a function of time over the domain from 0 to 5 seconds. So the object was not moving forward in the first second up until this point, let's say 1.1 seconds. It was actually moving backwards. And then from that point where it crosses the x-axis and where it has positive velocity, you could see how the object had positive, it was moving forward basically, it had positive velocity. So this is very important in terms of trying to figure out some of the questions we want to answer. For example, in example 2, suppose that the initial position of the particle at time equals 0, S stands for position, is equal to 9. What is a particle's position at 1 second? So what we'd want to do, essentially, is we would want to add this shaded area from 0 to 1 for the particle. So we want to integrate under velocity from 0 to 1, and we want to add to that the position at time 0. To get its new was if we integrate from 0 to 1 underneath the velocity curve, and we add to it the initial position, we'll find where we were at, or where we are at 1 second. So let's find the area under the curve. Integrating t squared minus, I think it's 8 over, let me just check the function, 8 over t plus 1 squared. If we integrate that from 0 to 1, we should get the amount of change in position. So I'm going to pause the video, and I'd like you to try to do that. It's a nice simple integral for the first part. The second part, I would suggest thinking of a substitution method, and then we'll regroup. Okay, so we're back, and I anti-differentiated the function, and it's t cubed over, the antiderivative was t cubed over 8, I'm sorry, t cubed over 3 plus 8 over t plus 1. So then I evaluate the upper limit and the lower limit, and I end up getting a net area of negative 3.667 meters. Now, the negative means that it lost position. So if s of 0, if it originally was at 9, and then I did the integral from 0 to 1 under velocity as a function of time, dt, this tells me the net change in position was negative 3.667. So it went backwards essentially from 9. So the position at 1 is equal to 9 minus 3.667, which is 5.333 repeating. So where is the object now at 5 seconds? To find the net change over 5 seconds, you would just find the integral from 0 to 5 underneath the same function, t squared minus 8 over t plus 1 squared dt. And this is the same antiderivative as what we had before, t cubed over 3. Now, mind you, if you can't do the antiderivative, you can still participate by simply using your graphing calculator to integrate between those two. The antiderivative 5 would be 125 over 3 plus 8 over 6. That would be the antiderivative 5. The antiderivative 0 would be what we had before, which was 8. And now I need a calculator to help me out with that because I'm not so good with, well, I could try it out. We have 250 over 6 plus 8 over 6, which will give us 258 over 6. 8 converted to 6 is 48 over 6. So I'm going to subtract that. And that what I get as a result is 258 minus 48 is 210 divided by 6, which is 35. So what this means is my net change in position from 0 to 5 was 35 units. So at time 0, I was at 9. At time 5, I am now at 9 plus 35 because this was my net gain in position. So that would be 9 plus 35 would put me at 44 for my position. Now, let's take a look at the next type of question, total distance traveled. Well, when you want to find total distance traveled, that's not the same as net position. Total distance traveled is basically, if we go back and we look at our graph, this distance that was traveled backwards up until this point is considered to be distance traveled, and you want to add that to this position. So how would you handle that in terms of integration? Well, if you were doing it by hand, you would calculate this area by using, you'd calculate it and it would be a negative area, and it would be like negative 3.667. And then you would, actually it's a little bit more than that. And then you would use this area and you would add them together as absolute value. Well, if you want to handle it in terms of finding net total distance traveled, you can just integrate the absolute value of the velocity function. And this I will show you how to use a calculator for. So from 0 to 1, or from 0 to 5, I should say, we're going to put into our calculator the integral of the absolute value of t squared minus 8 over t plus 1 quantity squared dt. So what I'd like you to do is try to program that into your calculator and find out what the area is from 0 to 5, and then we'll come back and talk about it. And that will give you the total distance traveled from 0 to 5. Okay, so I'm back, and with the graphing calculator, I got the value of 42.5868 meters. Now remember, we're trying to figure out in this problem what the total distance traveled was. So that means the backwards distance plus the forwards distance. So that's why we integrate the absolute value of the velocity curve with respect to time. Remember, you could have done this with your calculator and you could have programmed that in. So let's now take a look using these same concepts at an example problem that we're going to see in tomorrow's classroom set. Remember, the most important part is, can you take the velocity function and can you come up with a graph of it? Because that will tell you how to figure out when the particle is moving to the left or to the right or stopped altogether. So what I want you to do is remember back to pre-calc and graph this function on the domain from uh, 0 to 3 pi. So I'm going to put in um, some tick marks here, and I'd like you to graph that 5 cosine of t function. Okay, class, I'm back, and determine when the particle is moving to the left, right, or stopped. So this is the velocity function. Well, it's clearly moving to the right from, so it's clearly moving to the right when the velocity is positive. So that would be on the interval from 0 to pi over 2, from 3 pi over 2 to 5 pi over 2, which is in this region. And that's when it's moving to the right. Where it's stopped, it would be stopped at pi over 2, 3 pi over 2, and 5 pi over 2. And where it's moving left is when the velocity is negative, and that is when it is moving from pi over 2 to 3 pi over 2 and 5 pi over 2 to 3 pi. So that's when it's moving left, right, and stopped. So now the next question says, is what is a particle's displacement for the given time interval? Well, the time interval is from 0. The time interval is from 0 to 3 pi. So all we have to do is integrate the function from 0 to 3 pi under the velocity curve, and that will tell me what its displacement is. It won't tell me where it ends up. It will tell me how far it moved from where it started. So I could just simply integrate 5 cosine of t from 0 to 3 pi. And remember, we do this by using the antiderivative. So we have 5 sine of t. We're going to we're going to evaluate it at 3 pi and then to 0. So that's going to say, well, I need to know what 5 times the sine of 3 pi is, and subtract from it 5 times the sine of 0, and this will tell me the sine of 3 pi is equal to 0, and the sine of 0 is equal to 0. So guess what? In this case, my net displacement is 0. Well, let's analyze that to make sure. It starts out moving forward at about this area, and then it looks like it cancels out right about here. Then it goes back a little bit more, and then it cancels out in this region. And it looks like all the area balances out to where it ended up where it started off. So that's really, really interesting, and that's absolutely true. So its final position is where it started. So S at 3 pi is equal to 3. But now, what if the question then asked us for to find the displacement from 0 to 2 pi? This is what I'd like you to answer tonight as part of your homework. I want you to find out the answers for part A and part B again, but on the time domain from 0 to 2 pi. Tell me where the particle has ended up. I hope this video has helped, and I apologize for some of the technical difficulties, but good luck, and I look forward to hearing your feedback.